So thank you all for sticking around for the last lightning round talk of the forum. There's another one going on in the parallel session that primarily involves students working with Mihai Arani on dust. So if you'd like to hear their lightning talks, they are in the ballroom going on right now. This is the list of lightning round speakers for this round. So if you are in the audience, would you please go ahead and step to the front, and you can maybe over here on this side. That would be fantastic. And just as a quick reminder, the lightning round talks are 2 minutes long, and I will stand up at 1:30 to let you know you have 30 seconds left to wrap it up. And most of these people are giving posters, so please visit them at their posters afterwards. There is a poster session from 5:30 to 7 with a no-host bar, and as you might expect, lots of food. That's what we do well here, is feed you guys. So we're going to go ahead and get started with Rosemary. Go ahead.
Hi, I'm Rosemary Killen, and I'm at Goddard Space Flight Center. I'm really representing the DREAM team, which is one of the NASA Lunar Science Institutes. And the work that I'm talking about is poster E13. It really is a result of what we called a lunar excursion workshop that we had at Goddard about a month ago. And what the poster says, it says something like space weathering, but the reason I wanted to talk about it is that it really wound up being much more than that. The purpose of the workshop was to look at what happens when a coronal mass ejection goes past the moon. And so my part of it was to look at the solar wind, the sputtering, and we only looked at the sputtering component of the lunar exosphere. And we also, in addition to looking at the exosphere, I simulated the direct ion sputtered component, and then we looked at the photoionization from the exosphere. And then Pavel Travnicek took the ions and fed that into his hybrid model. So it turned out to be a really, really interesting study. And I have some movies of what happens, but I can't show them. But it turns out that you get about a factor of 50 enhancement in the exosphere when the coronal mass ejection passes by. And it was just so dramatic that I wanted to encourage everybody to come by and see our poster. We did sodium, potassium, magnesium, and calcium. And each one of these different species has a different morphology in the exosphere and reacts a little bit differently to sputtering. So please come by. It's poster E13. Thank you.
Hello, everybody. As you can tell, I'm not Nancy Shanover. She couldn't be here this afternoon, so we're filling in and talking about our poster for a little bit.
Yeah, my name is Chaz Miller. I'm a graduate student at New Mexico State University. Nancy is my advisor. We represent a team that observed the El Cross impact with facilities at Apache Point Observatory and Las Cruces. We had 3 telescopes, 3 cameras on 3 telescopes for the impact. One of them was a science camera on a 3.5-meter telescope at Apache Point. We had 2 video cameras. The science camera is visible light. We had 2 video cameras also going, 1 visible light on a 1-meter telescope and 1 infrared on a 0.6-meter telescope. Like everyone else, we didn't see anything when things first happened. We went back and analyzed our data, and we have a paper coming out in JGR this year showing our observation limits. So we actually looked at our 3 sigma noise limits levels inside the crater and made maps of that calibrated to magnitudes per square arc second to determine that our visible light limit was about 9.5 magnitudes per square arc second. We did some analysis with some assumed geometries of a high-angle plume based on the science papers that were released by the El Cross team to calibrate what they saw looking down with what we saw looking sideways, and determined we missed that by about 2 to 4 magnitudes per square arc second, depending on which geometry you choose. So our initial conclusion was in that paper we couldn't quite see it with the observations we had to the 3 sigma limit. However,
so in the 30 seconds I have left, I guess, after talking to some other grad students, we came upon another method, and we actually think we do see the L-cross plume in a new recent analysis. Our poster is E3. Chaz and I will be there right after this, and we'll also be around tomorrow morning. But we think we do see a plume. The plume geometry that we measure, we actually see it at the right time, in the right place, and it's the right duration. So we really think we actually can see it. And I'm out of time. Thank you.
Hello, my name's Vince Eek. I work at Durham University, and my poster is about what the LEND collimated sensor for epithermal neutrons actually measures. So if you look at the omnidirectional LEND detector, the map of the whole moon that they've made, and compare it with the collimated detector map, you would anticipate that the collimated detector should be a sharper version of the same map that you've got from the omnidirectional detector. When you do this comparison, it's plain that they're quite different qualitatively. So the collimated detector is actually measuring something different to the omnidirectional detector. And looking at the higher energy neutrons from Lunar Prospector, the map from the collimated LEND detector is much more like these high energy neutrons. So these are the ones that come through the walls of the collimator. So the poster that I've got has essentially a likelihood analysis that shows that about 10 times as much uncollimated lunar flux gets into the so-called collimated detector as collimated lunar flux. Now, this is a first, because Lunar Prospector didn't make a map of high-energy epithermal neutron flux from the moon. Okay, so there's a very valuable data set here. The compositional dependence of the high-energy epithermal neutrons is different from the low-energy epithermal neutrons, which is what Lunar Prospector measured predominantly. So consequently, there's interesting science that can be done with this data set, despite the fact that it's not predominantly collimated. Okay, thank you.
Hello, my name is Sonia Tiku, and I'm a PhD candidate at MIT working on lunar paleomagnetism with Ben Weiss. Basically, in the last few years, there's been a new revival of lunar paleomagnetism. There have been a few studies published within the last few years, including kind of the presentation that Clement Suave made yesterday on Apollo sample 10017, that show that there are a few lunar samples that have very stable magnetic records. And whenever you do a process of elimination study of like how these rocks acquire magnetization, it shows that these rocks most likely acquire their magnetization by cooling in the presence of a long-lived, stable lunar core dynamo field. So that's great. If there was a lunar core dynamo, that has great implications for the differentiation state of the moon and for the early, the thermal evolution of the moon over time. But unfortunately, what the case is that while there are a few lunar samples that have this good stable magnetization, the vast majority of lunar samples have unstable magnetic behavior. In the poster that I'm presenting today, C15, what I do is I address the unstable magnetization that we observe in many lunar samples. I explain why we see this unstable magnetization, and it's actually an intrinsic property of the magnetic carrier distribution in the rocks, which are mainly multi-domain iron for samples with poor magnetism. And since this poor behavior is because of this intrinsic thing to the rocks, it does not preclude the existence of a lunar dynamo. So we can believe the results of the stable magnetized rocks. You can't say just because there are some poorly behaved rocks, you can't rule out the results of the good ones. And so another side of this is, now that we know how to identify good samples versus bad samples to study, we can select good samples and continue to refine the time scale of the putative lunar dynamo and maybe extend it beyond what the current ages of 4.2 to 3.6 are. Thank you.
Hi, I'm Genesis Berlanga from Mount Holyoke College. I'm an undergraduate, and I've been working with Dennis Richards, Sanford Davis, and John Marshall at the NASA Ames Lunar Dust Laboratory in order to set up and develop a database of laboratory measurements for dust scattering data using various materials and lunar simulants. The experimental setup consists of a polar nephelometer that includes a halogen light source and a UV-VIS spectrometer. And it has the ability to sample various materials across a 180-degree phase function range. My work involved equipment calibration, software creation, in order to automate the spectral acquisition process and to improve the measurement precision and accuracy, as well as to enable in situ real-time data analysis and reduction with the software. This allows for immediate data plots even as you alter the experimental setup, which proved to be really useful to actually optimize it. The software is written in LabVIEW's G-Visual language, and it has various modes and capabilities for data reduction and data acquisition. LabDust data will provide an in situ reference for spectrometer behavior and aid in interpreting lunar atmosphere and dust environment explorer data, as well as in future missions. Ongoing and future work involves inclusion of a polarimeter to diagnose grain size, abundance, and geometry, as also the replacement of the halogen light source with a laser light source in order to improve signal quality and to extend the phase function angle range. And last but not least, to a greater sampling of dust material to increase the usefulness of the dust database and to aid in LADI data interpretation. My poster is in A11, and my email is on the bottom left corner. And thank you.
Hi, my name's Kristen Bennett. I just graduated from UCLA, and in the fall, thank you. In the fall, I'm going to begin my career as a graduate student at ASU. And this summer, I am working at Goddard with Tim McClanahan and the LEN team. We're working on correlating the diviner thermal data and the LEND epithermal neutron data that is an implication of water. And so we're focusing mainly on the permanent shadowed regions of the lunar poles, mostly because there isn't a good relation between water and the permanent shadowed regions. We don't really know what's going on. And so what we did to try to characterize this is our hypothesis was that there's a thermal condition that can relate those two. And so what we did was we averaged the diviner data, and then we averaged the LEND counts for each permanent shadowed region. And the correlation coefficient of that was about 0.42. And this is moderate to low correlation, but it's the same for the South Pole and the North Pole. And so this implies that there are similar geophysical processes that are driving the location of the hydrogen. And so they're similar for both the North Pole and the South Pole. And then, so we conclude that the, we conclude that the location of hydrogen is influenced by the temperature, but it's not the only condition that influences it. And so we're continuing to look at this, but my poster is at E20, and so I welcome any questions or comments, and I'll be there after this, so thanks.
Just a quick comment. There was a gentleman from JPL who also signed up, and I think his name got dropped off the bottom here. So if you are in the audience, you were officially on here, but I think he got dropped off. So I apologize. If you are here, go ahead and come on up.
Hello, my name is Stephanie Miller. I'm a recent graduate of Mount Holyoke College. I'm currently looking for PhD programs in chemistry for the future, but as of right now, I'm an intern here. I'm actually currently working in a Mars science group, but we won't talk about that today. Today we're going to talk about my work in a lunar dust group over in 245 with PI Claire Vickets. And actually, I was working more directly with Dr. Alessandra Rica in the supercomputing division. I was supporting her in some preliminary calculations for what you care about, which is a project on the chemistry of dust. Not so much investigated. There's been a lot on the physical properties, the composition, but what we're going to be looking into is the chemical activation of fine lunar dust specifically, and also what the passivation rates will be for when either, say, a human habitat on the moon becomes, if dust infiltrates that space, which we can assume will happen eventually, it's pretty ubiquitous, or contrawise, when dust comes in contact with the kind of vapors that we might be releasing in air or in rocket fuel exhaust. These are the kind of things that we want to really know what to look for, whether there's going to be explosions, toxic species created. There's another aspect of our research, which is a comparison of dust samples brought back on Apollo and dust simulant, JSC1A notably, which has very similar physical properties to lunar dust, being designed by engineers for technological applications in terms of mechanics, but not so much with chemistry. Most importantly, dust lacks reduced iron, which really, really affects the chemistry. I do not have a poster, but you can come and find me anytime. I have business cards and resumes, and those will have to suffice. Thank you.
Hi there, I'm Andre. I'll try to be quick. I'm Andre Bernier. I'm a recent graduate of Brown University, and I'm lucky enough to be working here this summer with Dr. Lynn Rothschild and others with the Brown-Stanford iGEM team. For those of you who are unfamiliar with iGEM, it stands for the International Genetic Engineered Machines Competition. It's a friendly contest hosted every year by MIT to encourage experimentation and collaboration in the field of synthetic biology. And we're really excited this summer because we get to work here and we get to work on space applications of synthetic biological systems. We think that there are numerous tools in the genetic toolkit that we can use to help space exploration and possible settlement. And we're working on 3 of them right now. The first of them is a biosensing project, kind of a canary in the mine shaft technique, where we can engineer these microorganisms to fluoresce. It's a resonant fluorescence in the presence of any variable that we deem necessary to monitor. That could be oxygen levels, that could be radiation and DNA damage, that could be temperature. And it's a way of monitoring the environment around this microbe, and we think that could be really useful. The second of our projects is a biocementation project. We're currently working with a small organism named Sporosarsina pasteurei that is capable of inducing calcium carbonate precipitation. And we're working with Lunar simulant right now, and we're actually getting very good results with basically making lunar concrete. We're approaching the strength, the compressive and tensile strength of concrete. Third and finally, we are genetically engineering a few strains of cyanobacteria that will be capable of producing and exporting sucrose into media for use by other heterotrophic organisms to subsequently produce any sort of pharmacological products, food, fuel, you name it. If you come talk to us at the poster, I believe we're C13, we'd love to chat with you, and it would fulfill every biologist's dream of being a geologist and planetary scientist. So thank you very much.
Andre, where'd you get that lunar simulant?
A gentleman here at NASA Ames named Dr. Brad Baker.
Thanks. And on the side.
Okay, I guess they did fill all the student slots, so that's good. I'm not a student, but I'm at JPL, and I was just actually a part of the group that's going to be doing the actual processing of the GRAIL, LGRS, and Earth-based tracking data to produce, numerically recover the full gravity field and the key parameters in the model for time-varying signature of the hypothesized solid inner core of the moon. And we've done an extensive amount of work in modeling and simulation and processing for this effort that's upcoming. And I have a poster here, number C19, simply covering some of that work that we've done. We've basically modeled all the relevant or significant dynamic error sources that we know of, and particularly non-gravitational accelerations, since Grail doesn't have accelerometers. And we've also taken a look at the various kinematic error sources. And so basically, if anyone has any curiosity or would like to know more about and gain an appreciation of all that we're going to go through to get the wonderful gravity field and interior structure model results that we all expect from Grail, then I would invite you to come by and chat. It's poster C19, and I'll turn you loose for getting some drinks. Thanks.
And what was your name again?
Oh, Gene Fonestock, JPL.
Thank you. So thank you all very much. I think the lightning rounds have been very well received across the whole conference. If you have any feedback for us on lightning rounds, please let us know. And thank you all for supporting these. These have been fantastic.